The substitution rule, also known as u-Substitution, is one of the pillars of any good Calc 1 class. And let's begin our discussion of the substitution rule with a description of the problem. The problem is that there's no chain rule for integrals. We have the chain rule for differentiation that allows us to take all kinds of derivatives, but there's no equivalent of that for integrals. In fact, here are four integrals that are quite easy to write, and the expressions inside the integrals would be very easy to take the derivative of. It would just be a quick application of the chain rule, and yet these integrals actually have no analytical solutions. The best we could do with these simple integrals, integral of sine x squared, integral of e to the x squared, integral of cos e to the x, integral of 1 over natural log x, the best we could do is come up with an approximation of what these things equal on a closed interval using a definite integral. And we do that using series, which you'll learn in Calc 2. So that's a long way of saying that in many ways integrating is much harder than taking the derivative. But all hope is not lost. Consider this example. Evaluate the integral of 8x times cosine of the quantity 4x squared plus 3 dx. Now this is something we can evaluate using something called the substitution rule, also known as u-Substitution. And the idea of u-Substitution is you're essentially looking for an integral kind of the form f of u, and then you want to have some kind of u prime outside of the function. So we're searching for a u that's oftentimes on the inside of the function and a u prime on the outside. And there can be constants, right? The u prime can be off by a constant somehow. It almost always is. And this becomes easier the more you do it. So the first few times you try the substitution rule, it's very challenging to see how these things line up. But after working several exercises, you start to really see the u pop out. So let's look at our example again. We're looking for a u and the derivative both in the same integral. And the u is probably going to be inside a function and the u prime will be outside. Well, look. Here we go. If I let u be 4x squared plus 3, then du dx is indeed 8x. Okay, so we decided u was 4x squared plus 3. And then we got our du dx to be 8x. And we essentially make a substitution. It's called the substitution rule after all. So one other thing we need to do here is we need to solve this equation for dx. So let's multiply up. That gives us du equals 8x dx. A lot of people just go straight to this, which we can then solve for dx. dx then is du over 8x. Now we plug this dx in up here for dx in the integral. And we plug the u in right here for u in the integral. And see what happens. This gives us the integral of 8x cos u, and then instead of dx we have du over 8x. And then look, those 8x's cancel, leaving us with simply the integral of cos u du. How nice. And look at that. That's something we can integrate. The integral of cosine is sine, so we have sine u plus c. But now, of course, we want to back substitute because we call that u actually equals 4x squared plus 3. This gives us a final answer of sine of the quantity 4x squared plus 3 and plus c. Don't forget your plus c. That'll do it. And if you're ever unsure about whether your integral came out incorrectly or not, you can always take the derivative of your result and make sure you get the original function back. So know that a quick mental derivative of sine 4x squared plus 3 does indeed give us 8x cos of 4x squared plus 3. So we are good to go. And that, in a nutshell, is the substitution rule. Let's try another example. Here we have the integral of the quantity 6x plus 1 times square root of the quantity 3x squared plus x dx. And again, we're looking for a u and a u prime inside the same integral. Oftentimes the u is inside of a function somehow. Maybe you see it. How about 3x squared plus x? If we let that be u, then note that du dx dx is simply 6x plus 1. Well, how nice. That's exactly what we have here. So we're on solid ground here. Let's solve this for dx. That gives us dx is then du over 6x plus 1. And substitute in for dx. Substitute the u in for u. And see what happens. All right, this gives us the integral of 6x plus 1 square root, and that's the quantity 6x plus 1 times square root of, well, u, and then we decided dx was actually du over 6x plus 1. Those cancel, how nice. And we're left with the integral of rad u du, which is actually the integral of u to the 1/2 du. Sometimes it's easier to integrate that. From here we use the power rule for integrals, which tells us when we're integrating x to a power, we add 1 to the power and then divide by that power plus 1. So in our case, the integral of u to the 1/2 du becomes 2/3 u to the 3/2 plus c. I added 1 to the power of u to get 3/2 and then divided by 3/2. But when you divide by 3/2, it's actually the same as multiplying by 2/3. But remember that u is actually 3x squared plus x. So we back substitute next to get 2/3 times 3x squared plus x, all to the 3/2 power, plus c. And finally, since the original integral was given with a radical, it's polite to give the answer also with a radical. That's just a certain formality. So let's do that. Our final answer would then be 2/3 times the square root of 3x squared plus x quantity cubed, and then of course our plus c's still hanging out on the side there. It's so easy to forget that plus c, so really try to remember that plus c is part of the answer for indefinite integrals.